We're transitioning more to something known as factorial designs. In this screencast, I'm going to talk to you about Introduction to Factorial Experiments. And we're going to be talking about factorial experiments in one way or another for the remainder of the class. Experimental design, this is also known as statistical design of experiments, SDOE, or simply design of experiments, DOE, is quite important for engineering and science. A lot of times in engineering and science, we have a process or a product, and we have several inputs. These are also known as factors. The process or product takes our input factors, and we end up with one or more outputs or responses. And you guys have already seen this when we've created mathematical models for different processes. Some inputs can be set or controlled while others cannot. The latter, the variables that cannot be controlled, are known as environmental factors. Some outputs represent primary product quality measures. Others relate to secondary constraints. In general, you're always trying to optimize some sort of process or product, the output. When you're just getting started, when you're characterizing something new, a new process or product, this is known as preliminary product process design. There are tens of factors, so there can be many things that you hypothesize that go into consideration for this process or product, and you need to screen through those to find out the important ones. At this point, only crude linear models are required. And then there's final product process design. After you've screened through your potential inputs that have an effect on your process, and you've eliminated the ones that don't have any effects, then you can go into kind of the optimization and final product process design. You've got a handful of factors, they're all important. And at this point, your mathematical models are more accurate. They're usually nonlinear models. So you've got quadratic terms, you might have interaction terms, and so on. And then finally, after your process or product is working, you usually have online optimization and control. This means that you have on-the-fly adjustments during production, and you're taking into account very small deviations from normal operation. So there's a need for minimal experimentation. Running experimental tests costs time and money. There's a practical need to extract as much information as possible with a minimum amount of experimentation. And you'd be surprised at how few people actually know how to do this properly when you get out into industry. A lot of people perform what we know as naive experiments or a naive approach, and these experiments yield far too many experimental runs. And I'll talk a little bit more about this here in a moment. Proper approach to experimental design is an absolute necessity in research and development, design, and production. This is not just important from an industrial perspective. Experimental design and optimization is also really important in academic research. So what is done in experimental design? We determine the factors that are going to be varied and the levels to be set for each factor. We determine the experimental plan, the schedule for experimental runs, and what the various factor levels for each run are. And finally, we set up the scheme for processing the experimental results. Experimental designs are sequential. You usually have a screening process. At this step, you want to screen through as many factors as possible, and so you don't want to put a whole lot of effort into these screening experiments. Once you've screened out the insignificant factors that affect your process, then you can go into final design, and this is more, you spend more time, collect more detailed experimental results, and you come up with a more accurate mathematical model. And finally, once this process is implemented, you might have control systems and you're looking for very small deviations from normal operation, and then you're making small corrections. So usually for screening, we go through something known as a fractional factorial design. For final design, we usually use a full factorial design of only those important factors that we identified in the screening step. And there's also something known as a central composite design that allows us to create a much more detailed mathematical model of our process. And there's lots of advanced techniques that are used for this online step that we're not going to talk about in this course. A lot of these advanced techniques are more industry specific. So where to start? We start with simple factorial designs. We can use ANOVA to determine significant factors. We can also use linear regression to determine simple models. You've already learned about the second two, ANOVA and linear regression, and now we're going to talk about simple factorial designs. It turns out that the mathematics of all three of these are identical, and I hope to show how we can arrive at the same conclusions using simple factorial designs, ANOVA, and linear regression. Let's talk real quick about naive designs and smart designs. Naive designs, this is what a lot of people do. They start an experiment. They might only choose 3 factors. They choose 10 levels for each factor. And they think that, oh, I have to perform an experiment for all possible 1,000 experiments of each of those 3 factors at each of those 10 levels. But this is usually infeasible. It costs a lot of money. It takes a lot of time. You might get a lot of data from this, but it doesn't allow you to quickly screen through those different factors. A smart design, this is a factorial design, you might choose something like 7 factors, so a lot more factors than in this naive design. The important thing here is you choose a lot fewer levels. So we might only choose 2 levels for each factor, maybe a high concentration of something and a low concentration of that factor. 2 to the 7th is 128. So we've performed far fewer experimental runs, takes a lot less time, a lot less money, but we can get out a lot more information than in this naive design. Furthermore, there's something known as fractional factorial designs. So instead of these 128 experimental runs, we could perform something like a half fractional design, and that would mean we'd perform only 64 experiments. And we'll talk about that in this class. So simple factorial designs, we usually have something known as L. This is the number of levels for each factor. We have something known as K. That would be the number of factors. And the total number of runs or experimental combinations required for a full factorial design is L to the K. I did mention a few minutes ago about fractional designs. Fractional designs would only have some fraction of these full number of experimental runs. Let's look at an example. You're trying to coerce stem cells to produce bone tissue. This is essentially what I did for my PhD thesis. You brainstorm that the following factors might affect production of bone tissue by the cells. So you got 5 different factors: dexamethasone, BMP7, beta-glycerophosphate, transforming growth factor beta, and maybe the percent serum. So we have 5 factors, K is equal to 5. Now a poor design would be to choose only 3 of those 5 factors and use 10 levels of each factor, and you would perform 1,000 experiments, and that's a lot of time and money. A smart design would be to choose 2 levels for all of those 5 factors. L is 2, K is equal to 5, and in this case you would perform only 2 to the 5th, and that's 32 experiments. Or, we'll talk later in this class about half fractional design. You could cut that in half and you can get almost as much information, especially during a quick screening experiment. So we could go through with only 16 experiments. That would cost a lot less money and time, and we get just as much information in at least a preliminary screening experiment than we would with this poor design above. And so in the next couple of classes, we're going to talk about how we can set up and perform these full factorial designs and these fractional factorial designs.